Have you ever pondered how extraordinary the abilities of animals can be during war times? In the summer of 1943, a pigeon named All Alone took to the skies on a daring mission. This plucky bird parachuted into France with a British agent entrusted with a task of paramount importance. All Alone was to deliver news of a clandestine military organization preparing for a wave of assassinations, the rounding up of Jews, and attacks on French resistance organizations. And deliver it did in less than 24 hours, the Allies were informed, enabling them to take prompt action. This was no ordinary bird, but a feathered hero that outstripped its peers in speed and precision. For this remarkable service, All Alone was honored with the Dickin Medal, a special award bestowed upon animals in the United Kingdom. This little pigeon's high efficiency and precision sparked curiosity among scientists. How could its navigation system be so powerful? Enter Klaus Schulten, a leading figure in biophysics who proposed an intriguing theory. Schulten suggested that pigeons are able to see magnetic fields, a phenomenon made possible by the curious world of quantum entanglement. At the heart of this theory lies a special protein found in the eyes of pigeons. This protein has an unusual relationship with light. When light shines upon it, an electron is knocked off from the protein molecule. This electron doesn't wander far. Instead, it attaches itself to a neighboring protein molecule. The twist here is that this knocked-off electron was originally entangled with another electron on the first protein molecule. This displacement causes the two protein molecules to become entangled. In the moments following this, the two entangled protein molecules participate in different chemical reactions, producing a variety of chemical substances. These substances are entangled themselves, and here's where things get even more interesting. These substances are extremely sensitive to the spin state of electrons, and different spin states make them appear different. Now, imagine a pigeon casually moving its head. This simple action changes its magnetic field relative to the Earth. These changes trigger corresponding changes in the aforementioned entangled electrons. Through the conduit of quantum entanglement, this can directly cause alterations in the chemical substances in the pigeon's eyes. This sequence of events leads us to a tantalizing possibility that pigeons might have a true visual perception of the direction of the magnetic field. It's as if they have an inbuilt GPS powered by the strange and wonderful rules of quantum physics. However, Schulten's findings didn't stop there, leading to a fascinating re-evaluation of how we perceive the world around us. His research team later used supercomputers to analyze and simulate many biological models of chemical reactions. Their findings suggest that many phenomena in our world are essentially governed by quantum entanglement. This implies a radical new perspective on how we understand our universe. Quantum entanglement isn't just a bizarre theory confined to the realms of physics. It's at work in the world around us, and even in the eyes of a pigeon. Professor Schulten and his team took the theory of quantum entanglement further. They turned to the titanic power of supercomputers, using them to analyze and simulate a myriad of biological models of chemical reactions. What they discovered was nothing short of groundbreaking. Many of the phenomena we observe, they found, are fundamentally governed by the mysterious principle of quantum entanglement. But the revelations didn't stop there. The team went on to propose a theory that challenges our very understanding of the universe. They suggested that space as we know it might not exist in the presence of entangled quantum particles. This radical idea, if proven true, could revolutionize our understanding of the cosmos, shaking the foundations of physics and opening up uncharted territories of knowledge. All this sparked by the extraordinary abilities of a small pigeon. From the extraordinary abilities of a small pigeon, we are led towards a whole new perspective on the universe, all thanks to the curiosity sparked by a bird named All Alone. Picture a pair of entangled quanta, one on the Sun, the other absorbed by a plant here on Earth. When the Sun's quantum changes, it instantaneously influences its entangled partner in the plant, potentially driving processes like photosynthesis. Intriguing, isn't it? Yet, the current scientific consensus holds that quantum entanglement can't transfer energy, only quantum states. But consider this. Perhaps our understanding of energy is incomplete or even misguided. Could it be that the light warming your skin was, moments before, a pair of entangled quanta, and the warmth you feel, is it the result of an observed transformation of quantum state? So let's dive deeper into this cosmic mystery of quantum entanglement and explore how it could redefine our understanding of energy transfer and perhaps the very nature of our universe. What if, before a beam of light warms your skin, it exists as a pair of entangled quanta? What if the warmth you feel is the result of an observed quantum state transformation? But the mystery deepens. Why does quantum entanglement occur, and how can entangled particles influence each other instantly, regardless of distance? Imagine a pair of entangled quanta on the Sun. One of them embarks on a journey towards Earth and is absorbed by a plant. When the entangled quantum on the Sun changes, it affects the quantum in the plant, driving photosynthesis. This is a process of energy transfer. Yet the mainstream view is that quantum entanglement cannot transfer energy, only quantum states. Perhaps our understanding of energy is incomplete or even flawed. Consider a beam of light that hits us and makes us feel warm. That light is energy, but before it hits us, it might be an entangled quantum. It becomes light and energy when observed by us. The belief that quantum entanglement can only transmit information, not energy, stems from our inability to convert energy into quantum entangled states that can be propagated. Essentially, we're limited by our comprehensions of true quantum entanglement in this dimension. The intriguing aspect is that even if entangled particles are far apart, the state of one particle determines the state of its partner instantly. It's as if there's telepathy between these two entangled particles, with information transmission time always being zero. Yet, Einstein's theory of relativity tells us that nothing in the physical world travels faster than light. This conundrum led some scientists to theorize that distance doesn't exist for entangled particles. In other words, the spatial distance we perceive might be an illusion. Theoretical physicist Leonhard Susskind took this idea further. He used mathematics to propose that our world is a virtual reality. He pioneered the theory of cosmic holography, suggesting that objective reality does not exist. Although the universe appears concrete and solid, it might be an illusion. So, here's a thought for you to ponder. Could we be living in a two-dimensional plane, perceiving a world that's nothing more than a cosmic hologram? The three-dimensional world you feel and experience could very well be a real-time rendering of two-dimensional information by your brain. Consider the difference between a standard photograph and a holographic one. The latter not only presents a three-dimensional image, but also offers a full 360-degree view. In essence, each fragment of our universe could contain the complete image, much like a hologram. Now delve into the world of quantum physics. Ever heard of quantum entanglement? This principle describes how two particles, no matter how far apart, can be so closely connected that the state of one instantly influences the other. It's like a cosmic love triangle. Imagine your dream lover in the United States and your love rival in China. You might think that by placing them far apart, they can't possibly interact. But in the world of quantum entanglement, distance is irrelevant. Even if they are worlds apart, they remain in constant communication. Just like every fragment of a hologram holds the complete image, every particle in our universe holds a connection to every other particle. In this holographic universe, separation is a mere illusion. In a deeper reality, everything is interconnected. But what if there's more beyond our universe? What if our reality is just a sliver of something far grander, a super-universe that dwarfs our own? This super-universe could be a place where the basic particles that make up everything we know aren't separate entities, but interconnected parts of a whole. Imagine a place where the laws of physics as we understand them don't apply, where every particle, every atom, every molecule is interwoven with one another. In this super-universe, the concept of separation might not even exist. It's a universe where everything is intertwined, interconnected, and interdependent. In conclusion, our understanding of the universe could be just a fragment of a more complex, interconnected super-universe. After all, we might all just be holograms in a grander scheme of reality. This mind-bending proposition is the cornerstone of the holographic theory of the universe. It suggests that our world as we know it is a projection originating from a flat world and an overarching super-universe. This theory, if proven true, could potentially unify the seemingly conflicting realms of quantum mechanics and the theory of relativity. But what does this mean for our understanding of the universe, particularly the mysteries of black holes and dark matter? Imagine a piece of information entering a black hole, a point of no return where even light cannot escape. This is where the black hole information paradox comes into play, a conundrum that pits the very nature of black holes against a fundamental principle of physics. Information cannot simply vanish. Now, black holes are notorious for their uncompromising grasp. Once something crosses into a black hole's event horizon, it's there to stay. But if information enters this abyss and never re-emerges, doesn't that imply it's gone forever? That's where the paradox lies, a seeming violation of our physical laws. Yet, the greatest minds, including Stephen Hawking, didn't accept defeat. They crunched the numbers, examined the equations, and reached a riveting conclusion. The information doesn't disappear, it transforms. It reappears in a different guise on the surface of the black hole, the event horizon. But how can this be? The answer lies in the concept of holography. If we consider a black hole not as an insatiable monster, but as a holographic projector, the puzzle pieces start to fit. The black hole absorbs information, processes it, and projects it onto its surface in a two-dimensional form. It's a radical reinterpretation of the nature of black holes, but one that reconciles our paradox. So, if black holes are holographic projectors, what does this mean for our understanding of another cosmic mystery? Dark matter. Dark matter. An elusive concept introduced to explain why spiral galaxies exist. These cosmic bodies, with their swirling arms of stars, lack the necessary mass and gravity to hold themselves together, according to our current understanding of physics. Scientists, in their quest for answers, propose the existence of dark matter, a mysterious substance providing the gravitational force needed to keep these galaxies intact. Yet, despite extensive searches, this dark matter remains unseen and unproven. Now consider the holographic theory of the universe, a perspective that paints our reality as a two-dimensional projection from a super-universe. In this view, the force that binds spiral galaxies isn't sourced from elusive dark matter, but rather from the super-universe's holographic projection theater. In the holographic universe theory, the mysteries of black holes and dark matter may be not mysteries at all, but simply indications of a more complex, two-dimensional reality that we're just beginning to understand.